All right, let's go. So I don't know what time I set the homework schedule, but maybe it's over already or not. But yeah, it was around today. So was it hard? Was it not too hard? Okay. Yeah, 3 was hard. Okay, so we'll see. I'll discuss when I've seen a bit the results. Yeah. Yeah, it's quite late. It's after the break. Yeah. Yeah. Because yeah, this whole matrix business is quite long. So and I feel like it's good to see all of it before. So you have another. I feel the population in the class is a bit heterogeneous. So some of you have already done a bunch of matrix algebra, maybe calculus. For some of you, it's quite new. And this class essentially is a grade leveler. So the goal is to put everybody at the same level. But still, if I just repeat everything word for word that some of you have already learned in other classes, you're probably going to get bored. So I sort of reworked the material yesterday, and I think it's going to be a neat way to present it. So here we go. It means though we have a lot to cover. So I just remind you what we were discussing last time. So it's just the start of the chapter 5. So consider a 2x2 system. Here is a matrix representation of it. So I have two coefficients for the first equation, two coefficients for the second equation. And then we have seen that the problem with solving this really comes from the fact that, for instance, the first coefficient is a fraction. So you can multiply the first line by a certain constant and get the second line. And with that, you get into trouble. So either you have no solution on an infinite number of solutions. So here's a small demonstration of this. So imagine that A1 times some constant lambda gives you B1, and A2 times some constant lambda gives you B2. So then you can just take the ratio there and you get this. And by the way, it would be the same if I said something like A1 over A2, A1 over B1 equals A2 over B2. So that would be the same problem. So here it was just, I could just as well multiply these by some fraction and got these, for instance. So the problem really is the link between those two. If they are proportional, then we're in trouble. And so we can essentially obtain this expression there. And I already said what this was. Do you remember? No, don't remember what this is. A1 B2 minus B1 A2. Right. So anyways, we're going to learn that today. So A1 B2 minus B1 A2. Is called the determinant of the matrix. So this matrix there. And we may note it this way. So simply we replace the brackets with vertical lines. And this is an important concept. We are going to, of course, to discuss it later. So now let's go to higher dimensions. So let's go to R3. So in R3, a set described. So R3 is where everybody lives. That's where we are in 3 dimensions, where there's time too, but physical dimensions. So a set described by one equation is what? Somebody knows? Somebody who has already done a bit of linear algebra? Or one linear equation. Could be one equation, but one linear equation. No? So in R3, a set described by one linear equation is actually a plane. So you would write it this way, for instance. So now it's a tuple of 3. So let's say it's x, y, z, such that, for instance, and then let's have just general coefficients. So a1 x 1 plus, yeah, do I use x1, x2? Yeah, sometimes we will use x, y, z. So a1 x plus a2 y plus a3. So this is a 3 equation, yeah, 3 variable equation. If I only have 2, then this is a line because it's a relation between x, y, and z. But here, since I add a third component there, then you can imagine that I could like go in the 3rd dimension as far as I want and essentially have an infinite amount of different lines. So if I set z equal to 1, then this is like one constant. If I set z equal to 2, that's another constant. So essentially, this whole equation describes describes a plane, a straight plane. And then if I set a set that's described by 2 linear equations, or 2 that, then let me add independent, which we're going to see what this means later. Is what? So that would be, for instance, and P1, 3. Oh, yeah, that's equal to A4, sorry. Yeah, otherwise it doesn't mean anything. So A4 and B4. So what did I do by adding a second one? So I said in the first case, it can be any triple of numbers, x, y, z, such that this equation is satisfied. Now I'm saying it's x, y, z such that this first equation is satisfied and this second equation is satisfied. So what am I doing? I'm adding more restrictions there. So intuitively, what do you think I should get? So imagine I have, or do I have a piece of paper? Somebody has a piece of paper I can be using. And somebody, can I borrow a piece of paper? So I said one equation, I have a plane. Then I add a second equation, and I am telling you, I'm looking for the set of points that will be to the first equation and the second equation. So what I'm going to get is the intersection of plane 1 and plane 2. What is going to be, what is this intersection going to look like? Yeah? Exactly. I'm just going to have, so imagine that you have a, say a box, and you have one side of the box is one equation, the other side of the box is the second equation. Then the intersection of these two sides is the corner. So this is exactly what I do. This is simply a line. And then finally, a set described by three independent equations, linear equation. Where am I going with this? Now I need more stuff. So I'm going to this one, and this one. So here it's yeah, again a set of three independent linear equations. So I want this to be true, this to be true, and this to be true. If they are all independent, what do you think I should get? I'm adding even more restrictions. Yeah? Yeah, a point. So it's, I have, say, for instance, if it's a box, I have the back side, the side, and the base. So they all intersect in exactly one point, the corner, for instance. So yes, this is a point. And then how would I, so this is, if I write it in as a set, but I can simply write it this way. So I can, let me write it in matrix form. P1, 2, 3. P1, 3. And C1, C3, which multiplies XYZ equal to 4. And so what does that look like? Well, let me show you the three independent planes I have and the intersection point. So I have it here. I'm just going to paste it. So here I have plane 1, plane 2, and plane 3, and they all intersect in this solution here. And all we care about all the time is finding a single solution to our set of equations. All right. So now let's talk about the topic that's been risen before, and I didn't address it properly. So linear independence. So what does it mean to be independent? Um, for vectors to be independent. Well, before answering this, I'm going to show you why we care about this, what could go wrong. So consider this, this set of equations. I would have x1 plus x2 plus x3 equals 1. And this, I'm going to say this is equation 1. Then I'm going to have two others. Equation 2 is going to be x1 minus 2 x2 plus 3x3 equals to 2. And then I'm going to have for equation 3, 2x1 minus x2 plus 4x3 equals to 5. So here I have a set of 3 linear equations, 3 unknown. So we should be able to do like we did in the homework assignment, to find a solution for them. So how to proceed? Oh, you should know it. Yeah. 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 So let's not go into matrices already, but yeah, we're getting there. So we know what we must do is, so let's, what did I, so let's try imaging x1. By the way, so here everything looks fine because this doesn't look like it's a multiplication of this one, and this one doesn't look like it's a multiplication of this one, and this one doesn't look like it's a multiplication of this one. So it would appear that we should be able to find a solution. So let's try it. So I'm going to take equation 1 minus equation 2. So if I subtract equation, if I take equation 1 minus equation 2, then x1 should go away. And then what I'm going to get is x2 plus 2x2 plus x3 minus 3x3 equals minus 1. So I get 3x2 minus 2x3 equals 1 Is it class related or? Well, you can like chat, but not too loud. All right, so this is what we get for if we do this. So let's try using equation 3 and 2. So what we could do is we have 2x1. So if I subtract minus 2 times this equation, I should be good. So minus 2 times. And if I do this, I'm just going to do this way. So I get 2. So this, of course, goes away. Yeah, no, I'll do it step by step to make sure I'm going in this step. So I get plus 4x2 here. And here 4x3 minus 6x3. And then minus 4. So I get minus 2x2. And here I get, oh, sorry, no, minus 3x2. And here I, no, 3x2, sorry, minus 2x3, minus 4. All right, so what should I do next? No clue. Should I just cry, go home? So I got rid of x1, but now I still have x2 and x3. So I have to find a solution for these. Yeah? Yeah, so if I do that, what do I get? I get 0 equals 0. So it looks like I'm in trouble. So it looks like I started with things that were different, but what is the problem? Well, if you look at it more carefully, you realize that equation 3, I just took equation 1 plus equation 2. So the problem is, it looks like I'm missing one equation. I can find a unique solution for x1. And what I did is the problem was that I had that equation 1 plus equation 2 equals equation 3. So I did that on purpose, of course. It was to mess with your mind. And you see what we get. So x1 plus x1 to x1, x2 minus 2x, x2 is minus x2, 1 plus 3 is 4, and 1 plus 2 is 3. So it looks like it's not enough for them to be independent by pair. They have to all be independent. And this is what we're going to see see later is linear independence. But But just before that, I'm going to show what this system of equations look like. I have it here too. See, I did a bunch of work yesterday. This took me a lot of effort, but so this is x1 plus x2 plus x3. This is the second one, and this is the third one. The second one and third one. And what you see is, well, it looks like the intersection between the first and the second is exactly the same as the first and the third and the second and the third. So if I think about my box again, I have one side, and then I just inserted another sheet exactly at the same place. So the three planes intersect exactly the same in the same region. So again, what does it mean? It means that what I'm going to find is an infinite number of solutions, is not enough information. In this case, they just intersected in one point because they were all independent. And here, they were all, each is independent of the others separately, but all three together, they're not, they don't, adding a third one doesn't add any information. So look at this carefully because I'm going to ask you to draw some of this like this at the exam. I'm kidding. I wouldn't dare even try myself. So there, but there's a nice website. I don't remember the name, but that I use, and you can draw these planes and these equations. It's quite neat actually. Yeah. So and note that. So question. What if I change rather than having this? What if I changed equation 3 from this to, for instance, let's have 410. So would I have been better off or not? So here I'm saying is, what if I change the intercept of one of the equations there? So rather than 3, I have 10, for instance. Would that help me or not? No idea. So in the 2 by 2 case, did it help if I change the intercept of one of the equations or not? No, it didn't. I could, if I had an infinite solution, it means that my two lines were the same on top of each other. And if I changed the intercept of one of them, then I shifted it up or down, but they were still parallel, and that was the problem. So here, what would happen? Well, if I change, for instance, so the third one is, well, I don't know what the third one is, but if I shifted the intercept of one of them, then I would shift that equation up. So the plane would change, for instance, or up or down, for instance. But in that case, what would I get? I would get a sort of one there, and one there. So an infinite tunnel where they never meet. So in that case, it's exactly the same as the 2 by 2 case. So changing, so no. Well, what if I change equation 3? So then in that case, we would have no. Or what I would have gotten is, say, instead of -1, I would have gotten something different. But so I would have had zero solution. Instead of an infinity of solution, I would have had zero solution. So the problem really lies into these coefficients there. The set of coefficients 1, 1, 2, 1 minus 2 minus 1, and 1, 3, 4. And how do we describe what it means to be independent? Well, it's what I must have is that no one equation can be reproduced or recovered from any of the other equations. So this is the concept of linear independence. Yeah. We need linear independence. So this is a concept that was in the book that's actually introduced in chapter 4, but I felt it doesn't mean anything to just introduce it. It doesn't ring a bell if you don't understand what's going on there. So let's go for it. Linear independence. And here's the definition. So this is from the book. I think I took it from the book. So a set of vectors. CV1 to the n. So it's perfectly general definition. Is said linearly independent if and only if any of them can be expressed. Yeah, so of course, yeah, so now I'm describing linear dependence, but independence is the opposite. So any of them can be expressed as a linear combination of the remaining vectors. Otherwise, the independent. So how do we operationalize this definition? So in general, vectors V1 to Vn. And here I'm going to give dimensions, but they don't matter. I'm just saying these are column vectors. So oh, I said m by 1. Yeah. Yeah. Sorry. Yeah, it's dependent again. If there exists numbers k1, ki, I equals 1 to n because I have n vectors, not all zeros. Such that, and here is how I would represent it. So simply the sum of I equals 1 to n of ki. Then I would have here my vector v. Equals, and then I would have a vector of 0. So here I write 0 n by 1. This means that it's a vector that only has 0. All right, so this is what it means in words, and this is what it means in math. So they are linearly dependent if I can find some combination of coefficients to multiply them, such that when I add all these combinations together, I get 0. So this is exactly like saying that here we found that equation 1 plus equation 2 equals equation 3, or rather minus equation 3 equals 0. The same idea. So here the case would be 1 plus, and here I would have 1, and here I would have minus 1. So there is some combination of coefficients by which I can multiply my equations to get all zeros. And this is the case for vectors. And then if the equation is that one is satisfied only for ki equals 0 for all I, then they are linearly independent. Because obviously, if I use all zeros, then 0 times the first one plus 0 times the second one plus 0 times the third one. So of course I'm going to get all zeros. So the interesting thing is if some ki's are non-zeros, and then I can combine them and obtain zeros. All right. So question about this concept. So you're going to have some exercise in the homework where I'm going to ask you, are some vectors independent, or how to make vectors independent or dependent? Yes. All right. So and now let's go to determinants. But before that, we are going to get there from this definition there. So example. So let's have an example with 3 vectors. Of dimension 3. So let's have V1. So I'm just going to write them horizontally, but use a transpose. A1, V1, C1. Transpose. So the only way I write this way is so that in the notes it takes less space. Then V2 will A2, V2, C2. And then V3 will be equal to So what we're saying is if they are linearly dependent, then what should I have? I should have that. So let's just use this formula there. So K1 times V1 plus K2 So let's write this just in terms of column vectors to be sure of what we're doing. So I would have K1. So let's just times A1 will be A1. What I mean, it's B1. C1. Okay, so essentially what does that mean here? Well, it means that I have three equations. K1 A1 plus K2 A2 plus K3 A3 equals 0. K1 B1 plus K2 B2 plus K3 B3 equals 0. And the third equation, K1 C1 plus K2 C2 plus K3 C3 equals 0. All right. And now we're going to see what does the end. I'm saying they are linearly dependent. So there's some here for some non-zero K1, K2, and K3 are all zeros. So what does that mean for the link between A1, B1, and C1, A2, B2, C2, A3, B3, and C3? Well, let's try to solve this. First equation, I have A1 plus K2 2 plus K3 equals 0. And then second equation is with the B's. And then third equation with C. Okay, so now what we want to do is to get rid of these. Essentially, we know that we have some set of K1, K2, K3 that's not 0. But what we don't really care about this. What we care about is what does that mean for the link between these coefficients there. All right. Did I make a mistake somewhere? Oh, yes. See, sorry. So we want to get rid of the K's. And note the following. So I could perfectly well divide by K1 all the three equations and get K2 or K1, K2 or K1, K3 or K1, K2 or K1. So I don't really need it essentially. K1 could be 1 because, yeah, after that, I could just, this is just some multiplicative, some multiplication that I have in front of each equation, but I could pretty much get rid of it already. So it's K1 to K1 equals 1. So that's less complicated. I would just redefine what K2 and K3 are, but it wouldn't change the relation I have with them. And now we have to get rid of K2 and K3. So we already said what we should do in that case. So there is one thing that could worry me is, for instance, A1, B1, C1, A2, B2, C2. I don't know what they are. Some of them could be 0. So if I start dividing by stuff, what I would have to tell you is, by the way, I'm allowed to divide. I'm assuming that they are non-zero. But there is a neat way to not care about, to not have to say anything about this by not eliminating by dividing stuff, but just multiplying. So for instance, what we can do is, oh yes, so this would be equation 1. Equation 2. And then let's compute. So let's get rid of, what did I do here? K2. So let's get rid of K2. So what I can do is multiply the first equation by B2. And then the second equation by minus A2. So, and add them together, all right? So if I do this, I'm going to get here K2, A2, B2. And here I'm going to get minus K2, B2, A2. So when I add them together, the K2 goes away. And I didn't have to assume anything about the fact that it could be 0 or whatever. So let's compute. K2 times equation 1 minus A2 times equation 2. If I do this, I get, so I want B2 times equation 1, so I'm going to multiply by B2 everywhere. And then I want minus A2 times equation 2, so let's add these A2 there. And then set minus there, minus this. And now what we do is we add them together. So minus A2, minus A2, minus this, and minus that. And lo and behold, this is what I wanted. So this way I have exactly the same term there, and I don't have any more. And let's just put that in parentheses. That's operator. This goes away. And here I have a term with just K3. Right. So I got rid of K2 this way. And let's do the same with equation 3, or let's use, I don't know, equation 2 and equation 3. So let's compute. And now I want to get rid of K2 again. So I'm going to multiply equation 2 by C2. So C2 times equation 2. And then minus B2 times equation 3. Same idea. So if I do that, I get C2. Yeah, let's put that later because it's C. And then minus B2. So let's add these B2 there. And I have minus and minus. And then let's add together. And as I was wanting, K2 minus K2B2C2 minus K2B2C2, this goes away. And let's just put these two together. This becomes 0. And let's have the K2. Okay, so yeah. So that was let's get rid of K2. So let's just say this equation is equation A, for instance, and we're going to get equation B. This is just to know what we're discussing there. So what should I do next? All right, let you copy. If I'm going too fast, tell me. Because this really is rather a demonstration of what's going to happen there. So it's very good because we're just fixing our algebra muscles. So it's always good to do all these things. But yeah, you shouldn't freak out about every detail, but it's good that you see where we're going. So what have we done so far? Well, I just said this could be 1, so we don't need it. Then we want to get rid of K2. This is what we did. Now, if we want an expression with just the coefficients there, so what step lies ahead? No idea. Okay, so I'll just move along then. So I wanted to get rid of K1, then I got rid of K2. Then what am I left with? Well, I have K3 here, K3 here. So I need to use these two equations there to get rid of the last. So now let's get rid of K3. And what we can compute is exactly the same thing. So we're going to here we want to have a term in K3 that's exactly the same in both cases by multiplying with something and then adding the two together. So what we can do is so what we can do is this times equation A minus this thing there times equation. And if I do that, well, I should have the same term for K3 in both. This is this is minus this and minus And then if I add them up together, yeah, I get something that's quite long. But the neat thing is that the terms in K3 disappear. So I'm just going to zoom out a bit. Yeah, so the terms in K3 are exactly the same. You see, A3B2 minus C2B3, B3C2 minus B2C3, and these are the same. So that, because that was my goal, so I end up with, so that's much simpler. What I can do is, let me present this in a, all right. So I get this. And so these are terms in so these are terms in four. We have four coefficients that are going to be multiplied by together. But this can simplify further. So because here I'm going to get yeah, I don't know exactly what I'm going to get, but it's possible to simplify them. So what I'm going to use is, so yeah, I could go over all the detail, but that's way too complicated for nothing. So this simplifies into this. And now I got rid of two terms. Plus here I can just divide by B2 everywhere. All right, so I get this. And this is what I wanted. So now I'm done. So sorry if you have, if I'm happy if you copy everything by hand, but know that I'm going to post that. So the goal was to reach this here. So where? This expression is the determinant of the matrix that would be composed of the three of them. Yeah, so maybe I won't yeah, I won't discuss this right away. I'm just going to leave it there. So this is the restriction and the question. So it means that if I add all these terms together and I get zero, I know that my vectors are not linearly independent. Okay. And the determinant. Let's form a matrix M, so it could be anything, with columns made of the vectors V1, V2, V3. We would have M equals. So let's put yeah. So these coefficients in my matrix. So I would have A1, B1, B3, and C1, C2, and C3. So the previous expression that we just found, this expression there, is called the determinant of M, which we write minus. So you have different ways of writing it, but yeah, this is a norm way in which you can find it quite often. It's like absolute value, the same symbol. So you would write it this way. So M equals. And now let's make some stuff appear. So let's group the AIs together. So we can express it this way. So let's put the A1 in front. And then have the A2. That and A3 at the end. All right, so yeah, I let you copy a bit if you want. And for those who are not copying, so think with me. What is this? What is that? And what is that? Does it ring a bell? B3 C2 minus B2 C3, B1 C3 minus B3 C1. No, no idea. So I just said that if I have a small matrix like this, A1, A2, B1, B2, then the determinant of this small matrix is A1, B2 minus B1, A2. So here, what does this look like? So this looks like the determinant of this matrix there. So B3, C2 minus B2, C3. Yeah, actually, I should let me put my let me change the signs of everything. That's good. Sorry for people who are copying. Of course, I just multiplied it by minus. Oh, and here I have a minus sign. Yeah, so I'm actually I want what I would like is to write this way. That's better. Because this is important later. So it's still true because here I have this equals to 0, so I just multiplied everything with -1. Oh, sorry, I screwed your notes. So that's why it's good that you copy it, but yeah, it's okay. Now I'm going to do it properly so that will be better. So this is A1 minus A1, and then minus A2, and then here I have minus A3. Okay, this makes me more happy. Here I have a minus sign there. A2. Okay, so note the factors that the AIs multiply determinant submatrices. So this is the B3, B2C3 minus C2B3, that's the determinant of this submatrix there. Yeah, so and B1C3 minus B3C1, that's B1C3 minus B3C1. So that's the determinant of a submatrix that would be made with column 1 and column 3. So what I'm going to do is just remove this column and this row there. And here B1C2 minus B2C1, that's this submatrix there. So this expression there is called what we call a Laplace expansion. Right. So, conclusion, in general, if a square matrix has determinants equal to 0, then its rows or columns in this situation form a set of linearly dependent vectors. And vice versa. All right, so this is the usefulness of determinants. So this tells you whether your matrix is well conditioned or not, whether you have enough information, whether what you're going to find is something that would look like this when you try to solve the system, or rather something that would look like this, or even worse if two planes are just the same. So something problematic, it gives you a 0 determinant. And something that works well, like this, would not give you a 0 determinant, would give you some positive or negative value, but non-zero. all right with this. So now I'm going to continue with some other properties of O. We go until, all right, so I'm just going to say a few things about determinants. And then we can continue later. So let's add some things. So the determinant of square matrix, only square matrices have determinants. Is written as I just said. Or sometimes you may see that. But I usually use this notation for one by one matrix. That would be like this, for instance. The determinant is just is simply A. And then Laplace expansion, which we're going to see next time, because that's a bit more, yeah, you need some time to think about it. But that's, it's going to look exactly like this. So, all right, questions, comments? I hope I didn't traumatize you too much. Just slightly. You should get over it.